Swayam Prabha. Digital India. Educated India.
So, today we will discuss a topic of interest, that is corrosion, which is a reality for any product. Reaction of the product with the environment is always there. The only thing is the outcome of all this is visible only after several years of use. Many times we find that the product which we have been using for several years has got rusted at places. At times it has undergone a change in color, it has say blackened. So, there are many ways in which this chemical change in the material manifests itself, and this is because of the reaction to the environment it is in. So, in service conditions, either a component is in contact with another metallic component, or it is in contact with another lubricant or any other chemical. It is in contact with oil, it is in contact with pure air or atmosphere in general. So, the working conditions could involve certain temperature, humidity, and of course, oxygen or exposure to air, due to which there is always a reaction between the environment and the product. Now, for example, this reaction is not apparent under room temperature conditions, but it is apparent in high temperature conditions. For instance, you have a hot corrosion of stainless steel pipelines taking place under hot conditions. Under cold conditions, of course, stainless steel is stainless, which means it is never going to get corroded. But at high temperatures, in the presence of certain gases, let us say sulfur dioxide or plus humidity, chlorine gas, humidity. So, all the environmental parameters taken together make an excellent recipe for a reaction of the environment with the metallic structural material. So, that is the reason why corrosion takes place, and this propagates. Now, corrosion does not necessarily mean oxidation. Oxidation is one chemical change that can take place. So, depending on the affinity of the material to oxidation, the oxidation will take place, but then corrosion is in general a reaction of the material or a chemical change the surface of a metal can undergo during the course of its service. Now, this chemical change can occur due to various reasons, because of its contact with another so called noble metal. So, let us see what we mean by all these terminologies. So, if you take the so called electrochemical series, what we find is gold has got the maximum positive potential, standard electric potential relative to hydrogen. So, if you form a cell, a battery cell with hydrogen as one of the electrodes and the metallic material as another electrode. So, the positive potential is generated at maximum positive potential generated at gold. So, 1.4 volts. Below that you have platinum 1.2, and this way you go on going down in this series until you come to hydrogen, where it is 0, and then these lead, for example, has got a negative potential. So, all these have increasingly negative potential. So, if you look at the alkali materials and alkaline earth materials, they are way below in the list because they are increasingly anodic in nature. So, they are extremely reactive, they are increasingly reactive, and they are increasingly anodic in nature. So, lithium would be further down here because it is again even more reactive as compared to these elements. So, the potentials or the negative potential will depend upon the anodic tendency of the material, and noble metals will be cathodic in nature, and so they will generate a positive potential. So, platinum for example is a noble metal. So, we know that gold is a noble metal, platinum is a noble metal, and in fact we make jewelry and precious items out of gold, and you know that gold never gets rusted, or you see that the gold never gets corroded. Comparatively, if you take silver, you find silver tends to get blackened. Silver reacts with the environment much faster and it tends to get blackened. That is because it reacts with oxygen, it reacts with the H2S gas, the hydrogen sulfide gas is also present to some extent in the industrial cities because of the flue gases from industrial processes going into the atmosphere, and so you have silver sulfide formation which is black in color. Similarly, you have copper undergoing a change. So, now copper is much more anodic as compared to any of these, and so the copper is much more reactive, and so all your copper utensils or copper articles have to be polished from time to time to get back the sheen of original copper. So, what we see is that as the material becomes increasingly reactive, it readily reacts with the environment. In fact, people say that water contained in copper vessel is good for health, and one way to understand it is that the copper kind of being anodic in nature purifies the water. So, if the water is acidic or it has some reactivity, the copper will readily react with water, and copper ions will get into water, and these when consumed in very small quantities might be good for health. Otherwise, generally people would not take excessive amounts of copper, otherwise it is bad for health. So, very small quantities of copper as one can have by virtue of putting water in a copper vessel for a prolonged duration of time can help in either purifying the water or having at least the copper ions inside it, which can be, when ingested, could be beneficial to the health. Okay. So, basically here what we are talking about is an electrode reaction with hydrogen as the reference. So, hydrogen is the reference electrode, and compared to that these are electropositive, and compared to that compared to hydrogen the rest of these are electronegative. Okay. So, now if we have to look at two different materials, not necessarily hydrogen now, let us say we have an electrode of iron and zinc, then zinc behaves more anodic with respect to iron, and therefore, it gives out electrons, and these electrons travel through the circuit, go to the iron solution. There is a membrane which separates out the which separates these two, and then allows only the zinc ions to travel. And so, what happens is zinc corrodes, meaning zinc gives out gives out electrons, zinc ions are generated, zinc twice 2 plus, and iron tends to electrodeposit. So, what happens is iron from this solution will electrodeposit. So, you have a solution containing zinc. So, on this side you have a solution which contains some zinc salt, here you have an iron salt. So, what happens is zinc ions keep going into the salt. This salt gets intensified in zinc ions, and here the iron ions get depleted and then they get deposited onto the surface of iron here. So, here the iron electrodeposits and zinc corrodes. So, this membrane makes sure that these two electrodes do not mix with each other. So, these two electrolytes do not mix with each other. So, why does this happen? Because iron is electropositive as compared to zinc. Zinc has got a negative potential with respect to hydrogen, so minus 0.763, and iron has got a positive potential of 0.771. So, the two together form a kind of a battery which will give out about 1.5 volts, right. So, that is the reason why that is the reason how batteries are constructed, or two different materials are connected in through a conductive medium, so that the current flows and there is a chemical reaction taking place at both these electrodes. Now, take the example of iron and copper. Now, you have different combination, you have iron and copper. So, you have iron having a positive potential of 0.771 and copper has a positive potential of 0.340. So, now what happens is that iron will tend to corrode. So, here in the presence of copper, iron will tend to corrode, and then there will be electricity flowing from here to here. So, now you have both are electropositive with respect to hydrogen, but then you have 0.771 and you have copper. Let us see where copper is. Okay, copper is here, it is plus 0.340, and so in spite of having a lower positive potential, the iron corrodes and copper electrodeposits. Now, we have common experience that if you take iron chloride and then put copper into it, I think you can precipitate out some copper. So, I think some such reactions we have seen in the chemistry lab, and we would trace them to this kind of situation. Now, so we have what is called as galvanic series, which tells us as to which metal is more reactive, more anodic, and which one is more cathodic. Cathodic means more noble and which will have some corrosion resistance. So, if you look at this series, on the top you have the increasingly inert, namely cathodic, and increasingly active will mean anodic in nature. So, we were talking about copper, and so this is copper nickel alloy. You have copper and iron. So, you can think of so iron alloy, that is stainless steel, is up there, copper and cupronickel are down there. So, cupronickel are much more anodic as compared to the stainless steel. So, what we see here is, I mean, this series is important because if one metal is more anodic with respect to other and two of them are in contact with each other, then the one that is anodic will start getting corroded. That is the point. So, many times what happens is we select metals for different components, and these components are put together and they are in intimate contact with each other in assembly. For example, you can have a threaded contact between the between two metals, and these two metals might be of different chemical composition, of different nature itself. Let us say aluminum in steel. Now, aluminum is much more noble as compared to steel. So, it has got so steel has got a much greater anodic nature as compared to aluminum alloys. So, so then what happens is the the corrosion will take place in steel. So, that is the thing. So, the cast iron and steel and aluminum alloys are very close to each other, and so if these two are combined together, then you can get some rate of corrosion. Now, farther apart is the are the two materials, greater is the rate of anodic corrosion. So, the rate of reaction is much higher if two metals which are far apart in this electrochemical series are in contact with each other. So, if you take zinc or magnesium alloys, sodium, potassium, etc., and then you put them in contact with silver or stainless steel, then you will have serious corrosion issues with the anodic material. So, that is something which one has to keep in mind. So, it is very important to select structural materials which are not aggressive with respect to each other. The structural materials do not behave like a battery, they do not create a galvanic cell as it is called. So, if you look at the galvanic cell and outcome of what happens when the galvanic cell gets formed, you have corrosion of the more anodic element. So, if coupling of dissimilar metals is necessary, choose that are close together in the galvanic series. So, it is very important. Avoid an unfavorable anode to cathode surface area ratio. So, what it means is that you have anode, if the anode is very large, okay, if the anodic area is very, very large, cathodic area is relatively small, then what will happen is the current density is something that is very important. So, if the area of the anode is large, so anode to cathode surface area ratio is high, then the current density is that much lower, and with a lower current density the rate of corrosion is also lower. On the other hand, if it is if the anodic area is very low, very small, and cathodic area is very high, in that case the rate of corrosion is high because a very high current density, the same amount of current is concentrated in a very small area. So, if we do not want this kind of galvanic corrosion to take place, meaning a galvanic cell to be formed similar to the battery cell which I showed you there. Now, here what acts as an electrolyte? The electrolyte is essentially the environment, especially the moisture in the environment. So, air surrounding this assembly, for instance, here what you see is that there is a steel core and there is a magnesium shell. So, steel core is embedded in a magnesium shell, and the magnesium shell is quite massive as compared to the steel core, due to which this galvanic coupling between magnesium and steel took place, and the circuit being so the circuit I am talking about is this circuit is completed through the atmosphere, because here you do not have any electrolytes as such, but then the electrolyte is the air with moisture in it. So, if you do not want corrosion to take place, if you do not want a galvanic cell to get formed between magnesium and steel, then first thing is avoid unfavorable anode to cathode surface area ratio, meaning the area of the anode should be as large as possible. Electrically insulate dissimilar materials from each other. So, if we do not have this circuit, this electric circuit, as long as we do not let this electric circuit get completed, then there will be no reaction here. So, when we want to make a battery, you need to make sure that this circuit is closed, because now you want control corrosion, and particularly if it is a rechargeable battery, you can get this anode material back during the process of charging. But so if you want to generate power, electricity the completing circuit is fine. But if you want to prevent corrosion, if you want to make sure that none of these react with the environment they are in, then it is important to disrupt this circuit, and that is the reason why you need to put these paints, that is dissimilar electrically insulate by applying insulating paints. So, these insulating paints like acrylic paints or maybe by design you can put a polymer gasket or some polymeric element between the two, so that the two get electrically insulated. Or one can connect electrically an anodic material to the other two. So, this is called as cathodic protection, because you have the anode being connected to or anode becoming a cathode. So, what you do is that you have another anodic material which is more anodic with respect to the metal which you want to protect, and then you will get what is called a cathodic protection. So, with respect to the third metal which is more anodic to the one which you want to protect, the metal which you want to protect will act cathodic. Normally it would not have been cathodic. For example, in this case what we see here, you have this as an anode, but now if you were to connect this to another element which is much more anodic with respect to this, then this will become a cathode, and therefore both these will get protected against any kind of corrosion. So, this is another way of reducing corrosion or protecting the material from corrosion. So, the simplest thing is that if you do not want this corrosive reaction to take place, I mean here the idea here is not to generate power, but to minimize the corrosion here and corrosion there. So, then what you do is you cut off this electric circuit, and if you have to cut off this electric circuit, there are various ways in which you can do it. You need to therefore disrupt the circuit by either putting an insulator there, or by making sure that the material that is anodic is connected to a more cathodic element, so that anode is connected to a more anodic element, so that the anode, the current anode behaves cathodic in nature. So, for instance, if you let us say we take a boiler, we take a boiler and you have water being heated in the boiler to high temperature, where the chemical activity of water is going to be very high. A boiler is made out of steel. You do not make it out of stainless steel. You make it out of what is called a boiler grade steel, which has got some corrosion resistant elements like close to 9% chromium and so on, but still that is prone to corrosion because of high temperature, high chemical activity of water. Now, if we have to protect the boiler from corrosion, what we do is we install a zinc plate inside it. So, what does a zinc plate do? Now, zinc is more anodic with respect to iron. Okay. So, zinc is more anodic with respect to iron, that is what is seen over here as well. So, when you operate the boiler, it is the zinc that will go into the solution, and iron will behave cathodic with respect to zinc. So, iron will behave like a cathode, and therefore, it will not get corroded. On the other hand, if you had not put the zinc plate, the boiler plate would have got corroded. Now, even in a single material, in a single material you have two different phases. We have seen that to develop structural strength you have two different phases which are formed. For example, in case of iron you have let us say ferrite and pearlite, right, or maybe you can have ferrite and cementite, or pearlite and cementite. So, you can have a variety of phases present in the microstructure of steel, and each one has got its own electronegativity. So, now if you take pearlite or if you take iron carbide, maybe it is more anodic towards anodic as compared to iron. So, you within the a given material itself, you have what is called as a galvanic cell getting created. So, even if you do not have anything else being remain in contact with the material, you just leave the piece of steel in air, still it will get corroded. Why will it get corroded? Because now you have two different phases having two different resistances to corrosion, and so one becomes anodic, other one becomes cathodic, and the atmosphere behaves like an electrolyte. So, the result is that the material gets corroded purely by exposure to humidity and air. So, basically to humid air. We always experience that corrosion is faster in areas close to the shore where the humidity is relatively high. So, if a city is situated close to the sea, then you have greater degree of humidity, and therefore, in the presence of humidity the rate of corrosion is much higher. In the interior of the city or away from the sea, you do not get corrosion to as severe an extent as you get in the coastal areas. In addition to that, you might have some salt, and I mean very close to the coast you could have sodium chloride in the air, and these chloride ions by virtue of presence of moisture will again attack the metallic materials, particularly the exposed metallic materials, and then react with them. So, the rate of corrosion is much higher in areas which are located close to the seashore as compared to in the interior of the country. So, basically the corrosion depends upon the degree of ionization of the metals. So, if you have greater ionization, if you prevent ionization, then there is no corrosion. So, the whole idea of disrupting this circuit is that you prevent ionization in the anode especially. When you have one single metal with multiple phases, and when you have each phase being anodic with respect to the other, then you cannot disrupt that circuit because you cannot put any insulator in between. So, naturally it is not possible. So, let us say tool steels for example have lot of alloy content. Tool steels have got lot of alloy content in it, and because of this alloy content you have lots of phases in tool steel which might be anodic with respect to the other phases. So, what happens there is you will have a galvanic cell set up and tool left in the air and in the presence of humidity will rust quite fast. So, many times tool steels are also seen to corrode quite rapidly. So, harder is the material, harder is the lattice distortion, greater is the state of energy of the lattice, and greater is the state of the energy of the crystal lattice, more efficient or more severe is the corrosive attack. So, that is what we find in our usual experience. What is oxidation? You have oxide formation, where again the metal gives out electrons here, metallic ions are generated, and these metal ions in the presence of oxygen and some moisture also, because then the transport of ions becomes easier through the moisture. So, half O2 plus 2E minus gives oxygen ions. So, then this M2 plus and O2 minus combines to make an oxide layer. Now, if this oxide layer is tenacious, so it does not allow any ions to pass through, as in case of aluminum oxide, then once an oxide layer is formed, there is no further oxidation. Similarly, chromium oxide. In stainless steels, the material remains stainless only because of the fact that once a chromium oxide layer is formed, there is no further oxidation. Otherwise, the material will continuously get oxidized, particularly if the oxide is porous. For instance, in case of iron oxide is very porous, due to which oxidation never stops. You see that the first layer of oxide that is formed, has M2 plus and O2 minus coming together, making an oxide of the metal, but then being porous, the air continues to have access to the interface, and as you get further and further exposure, the interior layers also tend to get oxidized because of the availability of oxygen and the availability of moisture and the conductive environment. So, the oxygen continues to move inwards through the porous medium, and the metal ions are always available in the presence of oxygen to react with it. So, basically the porosity of the oxide is a very important parameter in continued oxidation or even continued corrosions. For instance, corrosion products do not form a tenacious film, then what happens is it results in acceleration of corrosion, or it does not protect the material from corrosion. So, if the film is not tenacious, if it is porous film, then the corrosion products will continue to let the corrosive atmosphere in. The metal will continue reacting with the corrosion atmosphere, corrosive atmosphere, and finally it will result in continued corrosion. On the other hand, if the corrosion product is tenacious in nature, it forms a tenacious corrosion product, as in case of conversion coatings. For example, you do phosphating on steel. So, you have phosphating as a surface treatment which is given to many steels before it is painted. Now, this phosphating is basically so called conversion coating, which means that the chemicals which are deliberately added to the bath react with the surface of the metallic material, and this metallic surface undergoes a change in the chemical nature of the surface. So, which means that the surface forms a compound with the so iron will form iron phosphate, for instance, in case of phosphating. Now, this corrosion product, or not corrosion product, this reaction product, let us say, I mean this is all controlled corrosion only, but then since we want it to be that way, we call it as a reaction product. So, this reaction product is tenacious, and it will not allow continued oxidation of iron, continued reaction with the environment. Therefore, it will protect the material from oxidation. So, when we do the phosphating, it provides very mild resistance to oxidation, mild resistance to corrosion, and that is the way it does. Of course, the reason why it is why phosphating is done is because of the addition of paint. If you put paint onto it, then the paint adheres much better, and the paint is the one that gives the corrosion protection in addition to the aesthetic setting parts. So, the oxide formation or any corrosion process depends upon how porous the corrosion products or the oxide film that is formed on the surface is. So, if you have a high level of porosity in the corrosion products that are formed, the oxide film that is formed, the corrosive atmosphere continue to attack the metal and eat it very quickly. So, the metal will tend to get rusted, or the metal will degrade faster if the corrosive atmosphere or the oxidizing atmosphere is able to reach the metal faster. Now, the rate at which the corrosion will take place depends upon the chemical activity of the corrosive atmosphere as well. So, the chemical activity can be increased by the presence of humidity, for instance. It can also be increased by increase in temperature. So, if you increase the temperature, then the corrosive activity is that much higher. But then many times it has been found that humidity is the major player in enhancing the corrosive activity very rapidly. For instance, to transport hot sulfur dioxide gas. Sulfur dioxide itself is a pungent gas, right. It is a very pungent gas, and it is highly reactive in nature, but then if it has to be transported under hot conditions devoid of moisture, you can use stainless steel. Stainless steel 327 is used, and this stainless steel material has got a large amount of chromium in it. It's about 28 to 30% chromium. A significant amount of chromium is added in order to get the necessary corrosion resistance. But if there is moisture present, if there is moisture present in addition to sulfur dioxide at that temperature, so this moisture will of course exist in the form of superheated steam, and in a superheated condition this moisture will also behave like gas, but then in the presence of this moisture in an evaporated condition, this sulfur dioxide will have extremely high chemical activity, corrosive activity, and then it will react with the stainless steel, eating away the stainless steel very rapidly. So, hot corrosion. Now, especially in marine engines, for instance, you have sodium coming from the seawater, you have sulfur coming from the oil, that is a fuel. So, diesel, maybe diesel is used to run the engine. So, you have this combination, and you have stainless steel which is used for corrosion protection. So, the result is that whatever you do to prevent corrosion, particularly in case of stainless steel, turns out to be counterproductive under these hot corrosion conditions. So, hot corrosion is a completely different environment as compared to room temperature corrosion, because the chemical activity and the effect of moisture together form a very lethal combination to cause rapid corrosion in the material. Well, I was telling you that we use products for many years, and then over a period of time we find that they have got rusted at various locations. Now, crevices are among the major or the preferred locations where corrosion starts. So, especially if the environment is seawater. Now, seawater contains at least sodium chloride, if not more, because seawater is extremely polluted in nature. You know that all rivers end up into the seawater, and so the pH of the seawater is anything but 7. So, it is more acidic in nature because of presence of sodium chloride. So, as you see here, the corrosion starts in crevices, meaning where the exposure to air is practically nil. So, in a crevice the availability of oxygen is extremely small. So, what happens is that in the crevices the anodic metal will give out electrons, and these travel through the metal, come to the surface over here with in the presence of oxygen. So, wherever there is large amount of oxygen, they generate OH ions, so hydroxyl ions, and then you have these Cl minus ions going in over here, reacting with the metal. The metal gives up electrons. These react with the oxygen and oxygen ions, forming OH minus. So, you of course have water, and so these electrons coming here will generate, in the presence of oxygen, OH minus ions here. So, wherever there is oxygen that is available, you do not have any corrosion. Wherever there is less oxygen available, you have entrainment of these aggressive chloride ions, which will start eating into the metal over here, and there is nothing else to prevent that. So, that is the reason why we get what is called as crevice corrosion, especially when the two metals are bare. So, if they had been painted here, if this layer had been painted and that layer had been painted, then it would have been it could have been prevented. But normally what happens is when we tighten a bolt, let us say, okay, for example, these two are let us say these two plates are being fixed by rivet during and there is no paint in between, there is no material that will break the electric circuit or break the electric continuity. So, so what happens is the electric continuity still continues through this will still continue through the rivet even if you put paint or whatever. So, crevice corrosion becomes inevitable over here, that is because you still have elements which will result in completion of the electric circuit, that is the electrons being given away by given up by the metallic material here, and then these coming over here, these reacting with the oxygen present as well as the water molecules, and they together will form the OH minus ions here. You see that OH minus ions are formed here as well, and so there is a completion of the circuit. This chlorine gets ionized further and it goes in. So, you have more and more chlorine ions getting formed, and these chlorine ions, for instance, will get in and start eating into the metal over here. So, as the electrons come here, you have more and more chlorine ions getting generated, and these chlorine ions are always in constant supply, in continuous supply here. Now, this the metallic chloride again is not tenacious, it is bound to be porous, due to which there is an entrainment of the corrosive medium into it. So, had the layer of initial corrosion product been tenacious, it would not have let the chlorine ions go in, but since that is not the case, since the reaction product is also porous, it results in the corrosive medium seeping through it and then eating away a new virgin metallic surface that gets exposed after the previous round of reaction. So, gradually over a period of time this reaction progresses unabated. So, typically corrosion is found below the washers. So, this is the rivet, and the corrosion is particularly in a bolted joint, for example. This is a riveted joint, but in a bolted joint you have a washer, and then underneath the washer you see that the parent metal is getting eaten away. Similarly, pitting corrosion is another form of corrosion where the current density is very high. The pits are formed because the current density in the anodic area is very high. So, the size of the anode is extremely small, due to which the current density is more, and so a pit gets formed, and many such pits can be extremely dangerous. So, that is a very important thing to consider. The mechanism is for pitting is the same as for crevice corrosion, because again the once a pit is formed, the continuity of the reaction takes place by virtue of electrons being circulated through the metallic material. They come to the surface where no pits are formed, and then the medium gets ionized into, let us say, H plus and Cl minus or whatever, and then these ions further attack it in the pit, because now the intensity, the current intensity in the pits is that much higher. So, oxidation occurs within the pit itself. So, the metal giving up 2 electrons takes place in the pit itself, and the pit becomes deeper and deeper, and there is a complementary reduction taking place at the surface. So, the surface tends to behave like a cathode. So, the oxidation takes place at the anode and the reduction takes place at the cathode, meaning that the surface over here does not get corroded. So, that is what we were seeing over here. So, when electrons come here, the surface effectively gets reduced, and therefore, there is no loss of material from here. So, this surface behaves like a cathode. So, wherever lot of oxygen is available, it becomes a cathode, right. It will become a cathode. Wherever oxygen is depleted, where oxygen is much less, you will find that there it is an anode. So, if you take a threaded connection, where will the corrosion take place? Obviously in the threads, because the threads are the ones where you have least amount of oxygen getting access to it. So, when two metals are in contact, the corrosive medium that gets into the in between the two threads would result in a similar situation with the surface, the exposed part of the threaded connection behaving like a cathode and the threaded portion behaving like an anode. So, the result is that we always find that the threads are getting jammed. So, if you have not used something, or if you have not dismantled something or done and undone a threaded connection from time to time, you will find that the threaded connection gets jammed over a period of time. It gets jammed because of oxide getting generated at the interface. So, this oxide or these corrosion products, I mean it may not necessarily be oxide depending on the environment. If it is in the sea water or if it is in more aggressive environment, you will find corrosion products getting developed. Now, these corrosion products again will not protect the material because they are not tenacious, and as a result you will find that these corrosion progresses unabated. The volume continues can change. So, the corrosion products may have very much larger volume than the previous one. For instance, when you form iron oxide from iron, you will find that because of oxidation the volume has increased. Similarly, in case of many reactions, the reaction products have a greater volume as compared to the parent metal. So, the result is that the porosity, the film of the reaction products, or the film of oxide will be porous in nature, and that is the reason why the oxidation or corrosion can take place unabated. So, we have seen that oxidation occurs in the pit itself with complementary reduction and at the surface. It is supposed that gravity causes the pits to grow downwards, the solution at the tip at the pit tip becoming more concentrated and dense as the pit growth progresses. Actually, by gravity the solution might continue, the corrosive liquid might continue entering the pit because of gravity, and then it because of the pressure, now the height of the liquid column is increasing. So, the surface which is to be eaten away will have a big amount of liquid column on top of it. So, some effect of increasing pressure on the fresh surface that is being corroded will also play a role, and as the solution becomes more and more concentrated and the pit growth progresses, the rate of corrosion will also be that much higher, because now the corrosive attack, the current density is going to be much higher as the pit gets deeper and deeper. So, the cause could just be a surface flaw, a machining mark, a defect such as scratch or a slight variation in chemical composition. So, as I said, if you have two different phases present, one is more anodic with respect to the other, then that phase will get eaten away first. Now, if the phase gets completely removed, then the corrosion will automatically stop, but then if the phase does not get completely removed, it has its presence throughout the thickness, naturally you will find the corrosion progressing right up to the thickness and right through the thickness. So, that is why it is important that the metallurgy of the workpiece is chosen or is tailored so that there is no susceptibility to corrosion, right. So, any kind of corrosion, be it pitting corrosion, be it crevice corrosion, be it any other form of corrosion. Now, so one thing is have good surface finish in order to minimize corrosion, but then if you have on the exposed surface different phases, then they are again going to result in promotion of corrosion. So, this is what happens, I mean what I was just talking about happens in the form of selective leaching at times, because what happens is between two phases, one is extremely anodic, and when you dip it into a some sort of electrolyte, let us say in a liquid medium for instance, or even in a liquid medium, then one constituent gets preferentially removed, meaning it gets dissolved in it in the liquid medium, and so that is called as leaching. So, this is typical in case of brass type of alloys, where you have what is called a de-zincification of brass. So, essentially you know that 70-30 brass for example is 70% copper and 30% zinc, but then this zinc can get selectively leached out from copper. Now, if you look at the electrochemical series here at which we saw earlier, so you have copper over here and zinc over there. So, they are absolutely far away from each other, and then now zinc is much more anodic as compared to copper, and therefore you have, so some zinc is dissolved in copper, and then the rest of it remains, and so what happens is you have a loss of zinc to leaching. So, zinc is much more chemically active, it is more anodic, so it can selectively get dissolved. Okay. So, aluminum, iron, cobalt, chromium and other elements are which are vulnerable to preferential removal will cause selective leaching in those alloys. So, it all depends on what the other alloying elements are. So, the point here is that the selective leaching can take place depending upon the overall chemical composition, and the relative electronegativities, the relative behavior among phases, one phase behaving as anode, other one behaving as a cathode. So, whatever is now supposing something is highly reactive and it becomes anodic, then it can get easily leached away, meaning it can get dissolved in the in the solution, right. So, solution meaning in the liquid or in the corrosive liquid that is present there. So, then you will be left with pits from which zinc has been eaten away. Now, in the presence of a stress, the corrosive attack is even more severe. So, we have talked about the temperature, you have talked about humidity as something that aggravates corrosion. Now, there is another element that aggravates corrosion is the stress. I have discussed earlier that when a stress is applied, the stress fields of dislocations interact, the stored energy of cold work increases, especially where the deformation is very high, dislocation density is very high, or residual stresses are very high. There the stored energy in the material is very high, and in the process of reducing that stored energy, the corrosive attack gets promoted or the corrosive attack becomes easier. So, now for instance, if you have a certain degree of tensile stress, you have certain degree of tensile stress which is applied to the material, as you see over here while bending. So, this was a bar which was bent in a U shape. So, the tensile region is at the surface, or tensile strain occurs at the surface, and this is where most of the dislocation or most of the stored energy of cold work is present. Now, in the presence of a corrosive medium around it, the corrosive medium will only find readily find in fact a means of entering the metal or leaching away the metal, because whatever is at higher stress level or higher strain level or higher dislocation density level will behave anodic with respect to the rest of the materials. For instance, here if you look at this, there is no corrosion. That is because this is now cathodic with respect to this part. So, here it is anodic because very high stress is present, very high deformation is present, so large dislocation density is present, and especially on the outer surface there is energy of cold work that is present, and therefore the material can be eaten away relatively fast. On this surface, on the top surface, you see there is no corrosion. Why? Because this has been subjected to compressive stress. So, when there is compressive stress acting on the material, then you do not have any corrosive attack as such, but again if there is more is the stored energy of cold work. Now, we must understand that the tensile stresses tend to open up cracks, the tensile stresses tend to open up defects. So, the attack will be preferentially in areas where the tensile stresses are relatively high, and so that is where corrosive attack will be much more severe, and it will result in the relief of these tensile stresses. So, as the corrosive attack takes place, new surfaces are generated, and these new surfaces result in the relief of the stress. So, if there is residual stress, it will get relieved by virtue of generation of new surfaces due to corrosion. So, in brass for example, you have stress corrosion cracking taking place because this region was under high stress, and the corrosive element let us say the corrosive electrolyte found these highly stressed regions, high energy regions much more amenable for a corrosive attack. Now, all corrosive attack therefore happens at the grain boundaries. So, the grain boundaries are the ones which are attacked by corrosion. That is because grain boundaries are already regions of high disorder, they are regions of high energy, they already have large amount of dislocation density, and added to that you have a much greater energy of cold work that has been stored over here, meaning large plastic strain, the tensile stress that is present here is much more, and so the grain boundaries becomes much more susceptible to attack. Now, the difference between etching and corrosion is that when we want to reveal grain boundaries, we etch with a small say 0.5% nitrile or something like that, nitric acid in alcohol. So, we add very small quantity of nitric acid to alcohol. So, the idea here is not to corrode the material, the idea is to selectively etch the grain boundaries, meaning it is a selective corrosive attack which is intentional. So, some corrosion like phosphating, phosphate coating, etching involves intentional corrosion, intentional corrosive attack with a specific purpose for benefit of the user. On the other hand, what is objectionable is the unintentional damaging attack due to corrosion, unexpected attack due to corrosion, for which we would not have designed the product. So, that is where corrosion becomes objectionable. So, when we talk about grain boundaries get attacked by an etchant because the grain boundaries are regions of high energy. But then if the grain boundaries are if you leave the sample for a very prolonged duration of time, then the entire sample will get corroded, because once the grain boundaries have been attacked, the corrosion has taken place at the grain boundaries, then the rest of the material gets corroded. Now, while preparing a sample for metallography, supposing you have not polished it properly or maybe polished it with a very high pressure, it will have what is called a disturbed material on the surface. So, disturbed material means there is lot of sheared material, material which has undergone lot of shear on the surface, due to which when you etch the material or etch the polished surface, you will find that grain boundaries are not getting selectively revealed. What happens is the entire surface tends to get corroded, the entire surface tends to get etched. That is because of shearing, because of very large amount of force you might have applied, or because of very large local surface deformation that has taken place. There is a lot of stored energy of cold work. So, the difference in the stored energy at the grain boundary versus the grain interior is not much, and therefore, you cannot distinguish the grain boundaries properly as from the interior of the grain. So, that is again another outcome of the so called disturbed material which gets etched unintentionally. So, basically what I am trying to say is that the stored energy of cold work, because of presence of stress, the corrosion takes place and cracking takes place. Another means of enhancing the corrosion is erosion corrosion, where you have corrosion taking place and the corrosion products are eaten away, they are removed by erosive material, abrasive material. So, for instance, you have sand, or in air you have dust particles. So, all these tend to erode the metallic structure. The corrosion takes place, again the structure erodes the I mean the abrasive particles erode the corrosion products, the corrosion products get removed, and then you have fresh metallic surface getting exposed to the corrosive environment. So, this is called as erosion corrosion. We will discuss more about corrosion, corrosive mechanisms, how protection is achieved in the next class. Thank you.